Okay, thank you. So hi everyone. So I'm talking about this talk. I'm from Struers from Japan, and I'm one of the Ruby committer, the author of the current virtual machine. So I use the Ruby language to explain this presentation, but this presentation is not related to the Ruby language. So, and if you want, so this slide and my paper is published on this URL. Anyway, so today I want to introduce so today's question is how to make a interpreter very in easy way. So our solution is partial evaluation with very easy method. So we outsource any native code compilation to the C compiler, and we invented how to make a partial evaluator only with very straightforward, not complicated transformation. And another idea is naming the AST node with the Merkle tree to reuse the compiled code across the different processes. So let's introduce my motivation of this research. So of course, so maybe everyone understands this presentation. So this page. So if we have a program, so we translate to the AST abstract syntax tree, and so the most easy way to learn this program is tree walking interpreter that was used in Ruby 1.8 maybe 20 years ago. And after that, so of course it is slow, easy to develop, but it is too slow. So most of programming language, we invented the virtual machine here, and after that, the virtual machine is also slow, so we make the native code translation by the LT or just-in-time compilation that was introduced from the Ruby 3.1. So it is a very commodity strategy to make an interpreter faster interpreter, but it is too complicated to make this pipeline. For example, if we want to introduce a new syntax to the language, so we need to change the bytecode interpreter, and we change the native code compiler for. So it is too complicated, and especially I don't like to write assembler program anymore. So the question is how to make a fast interpreter. So thank you for yesterday's Professor Masahara's keynote. So partial evaluation is introduced. So the partial evaluation, with the partial evaluation, we only need to write the behavior of the AST interpreter, AST traversal interpreter here, and the partial evaluator specialize the AST interpreter with the given AST and make a optimized node. So the important example is the Trüff and Grau framework. So Trüff Grau framework provides partial evaluator for the Java program. So any target language, and the user only need to write a Java interpreter for this language. And the Trüff framework specialize this AST to the native to the intermediate representation, and the GRAL compiler compared to the native code. So highly optimized native code. That's great. So we only need to write the behavior of the each node execution. But so it solves my question. So the language, to make a language, so we only need to write behavior of the interpreter, so each node. But we need to use the Turk or a similar framework. So it is so huge infrastructure, and it is difficult to modify. It's difficult to use for me, especially so at least for me. So the next question is, can we make a lightweight partial evaluation framework? So for example, if we want to support the RISC-V assembler, RISC-V machine for the GRAL compiler, we need to spend many engineering effort to modify the GRAL compiler. So we need to get the way to generate a highly optimized code and widely available, so everyone can use, and they're easy to use. So the answer is, of course, the C compiler. So C compiler, of course, so in this room, I believe you can use the C compiler or C language. So it is very easy to use. Maybe. I'm not sure. But so our tool, ASTro, generates a specialized C code. And we can get a highly optimized code. So our tool, ASTroGen, written in under 500 lines of Ruby code, generates an interpreter with the specializer, the partial evaluator for the given AST. So we invented two ideas. So repeating that, so we invented our partial evaluator generates only specialized dispatchers, the tiny C snippets, and we can make a specialized C code for the given AST, and the code compiled for such a specialized C code, we can reuse it using the marker hash for each AST. So after the compiling, so we can use this compiled optimized code within another processes, interpreter processes, and so on. So this is a total workflow of the ASTro. So we need to we only need to write a node definition. So which nodes are there, and what's the execution behavior for this node, each node. And our tool, ASTroGen, generates many C source code, includes the definition of each node, the evaluator of each node, and the dispatcher for the evaluator function, and hash function, allocator function, specialized function for many utility functions. So of course, we need to write a parser for the language. I believe, so I understand that the many compiler classes in university, so it's spent many times in parser. So I believe that people can write a parser. And so of course we need to write a parser and make a AST for ASTro. And after that, the ASTro generated interpreter can run the baseline as a baseline interpreter. So baseline interpreter can run the target program P, but it is slow because it is only a tree-walking interpreter. But this baseline interpreter has a specializer for the AST, and it can generate a specialized C code. And specialized C code, so we can make the piece of the compiled optimized native code. And if we load this compiled code at the runtime, so it can be just-in-time compiler. And if we contain the compiled code with interpreter, it can be a simple compiler for the program P or a specialized interpreter for program P. So let's try to explain the ASTro framework with very small language. So we have three nodes, so num, add, and mul. So in the node def, so there is we need to start with node def. So it is a signature of the start of the definition. And the node nav is the name of the node. And so it seems a parameter, but it's declared that this number node has n field. So number node has the actual node the number information. And this explains the behavior of this node. So node num only returns the field number, and the node add receives a child node LV and RV and evaluates them and adding the evaluated results. So I think there is no question about that. So it is very easy to write. So ASTrogen generates the nodes, the header. So you don't need to write a header, so struct declaration anymore. So ASTrogen generates it automatically. And each node has a set of functions like dispatchers, specializers, and hash function, something else. And each node has the name of the dispatcher. So you don't need to write this kind of boring definition of the structures. And after that, ASTrogen generates the evaluator as a tree walking interpreter. So for our framework, we split the evaluation function to the dispatcher and evaluator. So evaluator, so eval, this one, receives the context, so that's language specific, and the node itself, and the extracted field, and the body of the behavior. So it means that so it's only copy the behavior, so there is no difficulties. And the dispatcher is a key idea for that. And this dispatcher calls this evaluation function with the extracted field. So in this case, dispatch node num extracts the number from the field, the node itself, and pass the node number, and run this code. So of course, this is very simple C code. So the C compiler can inline dispatch node num with eval node num. After so this is a internal node case, and it has only a bit trick. So not only copy the not only list the parameters of the node def, then it also adds the dispatch function for the child node. So all of nodes has a dispatch function. So we can get a dispatch function for this one, and so to invoke the dispatch node add function, then pass the child node with the function pointer to the dispatch function for the child node. So this function is passed, and the eval arg simply calls the corresponding dispatch function for LV. So in this case, so eval arg LV means calling this pointer with the context. So it's only small changes, and I think there is no difficulty too. So just now we have a tree walking interpreter, and we can get a dispatch function for the root function. So we only need to run the eval macro using the root dispatcher, root node dispatcher, and can run the tree walking interpreter. So it is only a tree walking interpreter. So it's still slow interpreter. So we need to introduce the partial evaluation. But before explain about the partial evaluation, so I want to introduce another concept, another idea. So marker hash. So marker hash is known as a tree hash algorithm for the tree structures. So for example, Git repository using the marker hash to maintain the Git repository. So in this case, so we can calculate the node hash value from the leaf node num 2, and this one 2, and so this node the hash value of HMAL can be calculated with each child node, and the same algorithm we can get all of the node hash value of the nodes. So the partial evaluation, so let's try to introduce how to make a partial evaluator for this on the ASTro framework. So we don't manipulate any method definition body, but only make a specialized dispatcher for each node. For example, if we want to specialize the node num, then we generate the dispatch function with the actual constant 2. So in this case, so the general one, it reads the number from the node, but we already know that the node number, the actual number is 2, so we can simply pass the number 2 to the eval function. So after that, we can get the dispatch function for the node num 2 and node num 3 for each dispatch functions. So we can pass the node specialized function for this one and this one, and for this actual AST sub-tree. So repeating this algorithm, we can get all of specialized dispatcher. And thank you for the C compiler. So if we pass the concrete program pointer, then the C compiler can inlining all of the tree, and then this code, so specialized dispatcher, only become returning the 7. So these 3 instructions for the Intel architecture. So this is what our specializer does, and we can get the compiled code for the AST, and we can get name for that. So okay. So with this idea, so we can make an interpreter for the simple optimization of the super instruction or super nodes, or compile program specific specializer interpreter, and the profile guided compiler, or just-in-time compiler. And the compiled code can be contained in a process, or we can put these compiled code outside of the interpreter, and the interpreter processes can share the compiled code. So we make a preliminary evaluation. So we make a very, very small subset of the Ruby, so named Ruby, not a Ruby, and without the object-oriented, so many rich functionality from Ruby. And it has 21 types and 300 node def definition. So we have to evaluate the dynamic language. So the function calling is lazy binding, and we introduce a call cache. And the call2 node assumes that the cached node can be a bigger AST. So it's I introduced this idea to evaluate the profile guided compilation. So we evaluate on the some setting with the corresponding C code with some C optimization flags, and also our compiled code can run on the disk file because we have a disk file C compiler. So checking the results, the interpreter. So compare with the tree walking interpreter, of course it is very fast, and the C compiler optimize the empty loops. So with the null operation, and the call operation can be optimized with the program guided one with the node call 2. So we have many discussion, but there is no time. So please see our paper. So we have many open questions and some limitation for this approach, and we have many related works. Okay, so conclusion. So we introduced the ASTro framework for the lightweight partial evaluator, and making so we can evaluate a preliminary evaluation with Naruby, and it demonstrates that the GCC, so corresponding GCC OZL approaching to this C compiler's C language's performance. Okay, so that's all. Thank you.
Okay, we have a couple of minutes for questions. If anyone has a question, would like to go up to the mic.
Thanks. Okay, thanks for your talk. So as you could know, so Truffle is now focusing on bytecode interpreters. So I'm curious about this approach is applied to bytecode interpreter generation. So how do you think about it?
Yeah, so because so the reason why we concentrate to the AST, because it is easy to inlining the functions. So if we get AST with Cora and Cori, so we can natively connect to the Cora subtree. So we can get a bigger AST without complicated things. So this is why we choose the ST for optimization. But of course, so we can calculate the hash value for the bytecode. So similar idea we can use, I think.
Okay, thanks so much.
Hi, thank you for the great presentation. Song from NYU. I had a question about your assumption that most languages provide an AST, because as far as I know, Lua does not have a AST definition, like does not have an external facing AST definition. I think Ruby also did not have like a unified parser until very recently. So is it true in practice that many of these interpreted languages come with an AST, or could it be the or could it be the case that languages actually kind of have converged on bytecode as some sort of unified interface for other interpreter implementations?
Yeah, I think it is an interesting idea, but I'm not sure we have the impact for such other languages. So I'm happy to get AST AST representation for each language, and I want to try ASTro framework for any other languages, but I'm not sure the people what the other language authors think about that.
Thank you.
Okay, great. I think we're about on time now. Sorry?
I actually have a question.
Oh, go for it. Please, go ahead.
Hi, sorry, I've left the mixing desk for 2 seconds. Thank you for a really interesting presentation. I'm Finn from the University of British Columbia. I'm curious what your thoughts are on memory management. I know for simplicity you skipped it in your evaluation, but given your dependence on C, which has no really helping for this, how would you add such a feature?
Right, great question. So I need to put the memory management on the open question. So for example, so using Java, so we don't need to have we don't care about the memory management because Java has a garbage collection. But I'm not sure the Java or other managed language, managed language can make a good performance. But so because we use for the performance reason, so we use garbage collection. We use a C compiler, C language to make this framework. But for example, so if so the answer is I'm not sure we can use the garbage collection managed language to use this one for the performance. But so for example, C-Ruby, so we are making a C-Ruby interpreter and written in C language, and we make our own garbage collector. So we can, I think that we can make our own garbage collection for that. But it's maybe it is a separate topic for the ASTro.
Thank you.
Great. Let's thank Koichi for a great talk. I think that we're out of time now, so we're going to move